Okay, so in previous lecture we discussed about Bragg's law and X-ray diffraction also. So from X-ray diffraction we know that why we use X-ray to study crystals, because their wavelength and the spacing which is available in between crystal planes, that is of comparable range. That's why X-ray can be used to study. Neither visible, UV, all this we cannot do. Now we have also known that what are the components required for basic X-ray diffraction. Like we need a source of X-ray, then we need to control the wavelength, and then we need some method so that we can detect that there is X-ray has been constructively interfered, because it is not visible with naked eyes, right? We need some indirect technique to detect this X-ray, and we need some method to read this spots, or whichever way we have identified the X-ray constructive interference. Now in this lecture series, fifth lecture, we'll discuss about various methods of X-ray diffraction, how they are different from one another, and is there any pros and cons of each of these method. Okay, so basically we'll discuss Lawy's method and powder method. Along with this, we'll also discuss Bragg's spectrometer. Okay, see, Bragg's law is the foundational law for X-ray diffraction. Now that is a law because it is a experimental validation, and this Bragg's spectrometer gives the validation, has given the validation to that Bragg's law in the beginning. Now this Lawy's method, powder method, all of them uses Bragg's law, but the Bragg's spectrometer was like the experimental method which was started in the beginning, right? So we shall move to our first method, that is Bragg's spectrometer. You can see from this diagram on the left that X-ray is coming out from a tube, and then they are made parallel via these slits made up of lead. We need to use some heavy metals because otherwise X-ray will penetrate through the metal. Now we have a circular, like this rotating apparatus which we can rotate and change this value of theta. If you remember, in Bragg's law we have discussed that like this two planes are there, X-ray incidenting on the here, getting reflected, another X-ray passing through to goes to the second plane, and then it gets reflected. This ray 1 and ray 2 has path difference of 2d sine theta, where d is the interplanar spacing, theta is nothing but glancing angle between the incident ray and the plane, okay, the crystal plane. So 2d sine theta if equals to n lambda, this is a condition for constructive interference. So this was discussed in Bragg's law in the previous lecture, no problem. So we need to know who is theta, who is d. D is interplanar spacing, lambda is the wavelength used, and n is the order. See, this is the first order. From first two plane only it is getting diffracted. So first order. You can go to the second order also, second, third, fourth, any order. Now let us move to this. This is our theta, because we have a single crystal in Bragg's spectrometer. So what kind of crystal do we use here? We use single crystal. Okay, so there is this crystal. If we rotate this whole table, if we rotate clockwise or anti-clockwise, this theta value will change. Now theta value will change, that means this 2d sine theta as a whole, this value also will change. Theta change means sine theta will change, as a whole this thing will change. So sometime at particular value of theta it gives a maxima, okay, at other value it gives minima, again it gives maxima, again it gives minima. So there are some specific value of thetas along which we get maximum current. What is this? Along y-axis we have current. How do we get this current? See, whenever X-ray this is diffracted or reflected from this crystal, they enters into an ionization chamber. What is ionization chamber made up of? It is made up of gas. The gas is filled inside. So when X-ray enters inside this ionization chamber, they ionize the gas. What is the meaning of ionization? They remove the electron from the outermost shell, so the electron becomes free to move. When electron becomes free to move, there is electrode connected here, so positive and negative. Electron is negative in charge, so they have attractive force towards the positive electrode, and there will be a current shown by this galvanometer. So if the X-ray intensity is high, ionization is high. Ionization is high means current will be high. So high current implies that X-ray has undergone their constructive interference. And if we repeat this experiment multiple times for a particular crystal, then this theta 1, theta 2, theta 3, wherever we got those maxima are constant. It is not like some accidentally we got those value. Repeatedly you do the thing, you will get the same result. So definitely there is relation between this glancing angle and ionization current. From which relation we can say this one? 2d sine theta equals to n lambda, that is Bragg's law. So from here theta value we can find from this plot of glancing angle along x-axis and ionization current along y-axis. Lambda value, what is the wavelength we have used, that is known. So considering if it is first order, then we can easily find the value of d. So that is how Bragg's spectrometer works. So most important thing we should note down here is what kind of X-ray we are using. We are using a fixed X-ray wavelength, so lambda is fixed here. Theta, what we are doing? Theta glancing angle, we are changing theta by rotating the circular table. Then how we are detecting whether X-ray diffraction, X-ray is constructively interfered or destructively interfered, we are using a ionization chamber. Okay, so and then we are also using here single crystal. So that these few points we need to remember so that we can compare with other methods, how they are similar or how they are different. So next, moving on to the other method called Lewis method. In this method, it is written we are using a white X-ray beam. Now white X-ray beam does not mean a white light, it's still X-ray only, but it has certain range, say 0.2 angstrom to 2 angstrom. So we do not use lambda same. Lambda is a variable here. But theta, that is glancing angle, is constant because we are not rotating the crystal. The crystal is firmly mounted on a handle. So theta is fixed. We are also using here single crystal. And how do you detect the X-ray? Previous in Bragg's spectrometer we use a ionization chamber. In this case we do not use a ionization chamber, we use a photographic film. Okay, so when X-ray, this white X-ray incidence on this crystal where theta is fixed, they for some value of lambda it gives a maxima, for some value of lambda it gives a minima. So those which are giving a maxima, there forms a dot on this photographic plate. If the crystal has some kind of pattern, that pattern can be studied from these spots. This is known as Lewis spot. Okay, so from this, if there is some gap or impurity in that crystal, we can find out from this Lewis spot. Most importantly, in Lewis method, we use single crystal, and then from here we can determine orientation of crystal and if there is any impurity in the crystal. Okay, orientation and impurity. Rather than the structure, we find these things more from Lewis method. So let us move to the other most popular method, that is powder method. Okay, so in powder method, lambda is fixed. Wavelength is fixed. We do not change the wavelength. That is not variable like in Lewis method. Then theta is a variable. Now theta is a variable. You might think we do not see here a circular table. How do you change theta? Because we do not use here single crystal. We do not use single crystal. No, we use here powder sample. Okay, so powder sample means in that sample, wherever you are placing the sample, there will be crystals but of different orientation in different space. Suppose here orientation is like this, here orientation is like this. So it's a combination of many crystal orientation. So when X-ray hits here, the theta is different for different orientation. So I'm placing, suppose, simple two example I'll give you. Here suppose two crystals are there, one with this orientation, other with this orientation. I'm incidenting X-ray here. So you see, theta is different for the top part and theta is different for the bottom part, although the direction of the X-ray is same, because the plane itself, the orientation of plane itself is different in powder sample. There are variety of planes orientation. Okay, so that is how theta is variable, because we are using a powder sample, not because we are rotating the sample. Okay, so we are using a powder sample, not single crystal. Next important point is, how do we determine that X-ray has undergone constructive or destructive interference? We use a photographic film only, but around the sample we mount it cylindrically like this. Okay, in that film there is a hole so that X-ray can enter and then hit the sample, and then they can come out through the exit hole. So the X-ray where X-ray is entering and coming out on a straight path like this, but because sample is there, they undergo diffraction. Some comes back reflected also, some gets diffracted also. So those which are constructively interfering, they gives us a spot on the photographic film. So wherever spot is there, that means they're constructive. Here there is no spot, that means all the their position of theta is giving us destructive interference. Now the point is, here also we will be using same Bragg's law, that is 2d sin theta equals to n lambda, and how we are going to find this theta and how we are going to know this n or lambda, all these things. Okay, so here lambda is fixed, as I said. Only in Lewis method we use white X-ray variable is there, but here lambda is fixed. So from the source it is known, lambda is known. Okay, now D is variable here. Why D is variable? Because we are using a powder sample, we are not using a single crystal. Theta is also variable again, because we are using a powder sample. So how we are going to find theta? Very simple way. Let us recall this one. If you know that if you have an arc of a circle, if this is the radius, and then whatever, if this is the angle made, theta, then theta equals to arc by radius. This formula is known from class 9 or 10 most probably. So that simple thing only we will use here. So you see, there is an arc length. How we are going to find? We will open this film. This is a gap. This is one time cylindrical. You can make it like a linear one. So this is the entry hole. This is the exit hole. Around this marks are there. This is one mark on the like this one is this mark. This one is this mark. The opposite side you have some marks again. So now what we do? We find arc length from here. Suppose this is from this center to this is x, this is another x. So this whole thing is twice of x. Okay. Now we can find the radius also easily from center, wherever your sample is placed, to this, whatever is the radius. So arc length is x, our arc is x, radius is r. But can we find theta here? Is it theta from center? This, like this we are getting, right? Like this. So this is suppose the exit hole. This is first from here to here, it is x, first arc. Now this will give us theta, 2 theta or 4 theta. That is a common doubt among students. So we'll try to understand from another perspective. See, so if we know the orientation of our plane, we know that this is theta, this is incident angle. If we extend this whole thing, this is also theta. If we draw, this is also theta. So whole thing is 2 theta. Okay, so this is the reflected one. This is the extended incident ray. Okay, this is most common viva questions also. If you go for PhD or such thing, this question is asked. Why do you use 2 theta rather than theta? See, 2 theta we use because we cannot find the value of theta in powder sample. We do not know where is this plane. We can know the value of 2 theta. How? You just extend the incident ray, and the angle made by the reflected ray and the extended incident ray is always 2 theta. Theta is variable, it is different for different planes, but you can tell that definitely that is 2 theta. Okay, so that's why from here this is the exit hole. Yes, like this is the exit hole, means what? X-ray incident, and it is coming out, so you can say this is the extended incident ray. This exit hole is nothing but extended incident ray. This reflected ray is nothing but this curve. So finally we can say that from this to this is actually, it will give us 2 theta. So if this arc length is x, radius is r, 2 theta equals to x by r. What is the unit of this theta? This is in radians, because we are taking ratio of the length, arc and radius, right? How we are going to find this in degree? How do we convert radians to degree? We'll just multiply 180 degree by pi. So like that we are going to find the value of theta. Once we find the value of theta, we can substitute in 2d sine theta equals to n lambda. Lambda is known. We can find the value of d. So we need to remember this few things in powder method. The plane orientation we do not know. That's why we find 2 theta. The angle from this center to this first arc is always 2 theta. From this, if you take from this arc to this arc, then it is 4 theta. Okay. So moving on to the comparison table between the 3 methods we have discussed here. Okay, Lewis method, rotating crystal method is nothing but you can say this is Bragg spectrometer only. Similar, okay, Bragg spectrometer. So in Lewis method we use a variable wavelength but angle is fixed, and we use a single crystal. Rotating crystal, wavelength is fixed but variable, angle we can change. It's also a single crystal. Why powder method is so popular? Because the angle is variable and we are using a powder sample. Naturally, whatever requirement are there to study crystals, they are generally not single crystals. They are most of the time polycrystals and powders. So since this powder method can study those kind of sample, it is widely popular these days. So that's it for this lecture. In the next lecture, we'll discuss some problems related to this unit.